Hi there, in this video we're going to have a look at Pascal's triangle expansions. I'll explain a little bit more about that as we go along, but before I do, let's have a look at what Pascal's triangle is. And it's a neat triangle of numbers that's generated according to a very specific pattern. Um, the top of the triangle starts with a 1 like so, and then underneath that we do another couple of 1s. So that's the top of the triangle. And then after that, we generate the next row of the triangle by starting with a 1, and then the next number is generated by adding the two numbers above it in the triangle. So I'll just color code them so you can sort of see it. That would be 1 plus 1, which is 2. And then when we get to the end of the triangle, we add another 1. I'll do the next row so you can see that as well. So we've got a 1, and then add those two numbers together to get 3, add those two numbers together to get 3 again, and then we've got to the end of the triangle, so we go for a 1 at the end. And I'll go one more line here, start with a 1. Maybe you might want to pause the video and then try it yourself. Okay, so it's 1, and then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then there's a 1 at the end. It's pretty quick to do once you are kind of in the zone to do it. You can generate it pretty quickly. In terms of organizing our rows, you can see that this row here has a 2 in it. If I go down here, you can see this row has a 1 in it, this has a 2 in it, this has a 3 in it, this has a 4 in it. So typically, we tend to say that this is the fourth row, this is the third row, this is the second row, this is the first row, and this is the 0th row. And that's the reason why we do that will come clear in a second. So let's have a look at this expansion here. This expansion is x plus 1 all cubed. Now, we already have a rule for a plus b all squared. That's the perfect square rule, and that's fine. That works perfectly fine. But we don't have any way of systematically figuring out what something like a plus b to the power of 3 or to the power of 7 or to the power of 11 is. The way we would do it is basically a longhand expansion. And to save time, I've just done this one already. I've gone x plus 1 all cubed. I've broken it down into x plus 1 multiplied by x plus 1 all squared. That's fine. That's something multiplied by something squared is something cubed. I've then used perfect square to expand it. I've then used chicken beaking or whatever you want to expand it further, and then I've collected my like terms here. So if this doesn't make sense to you, maybe pause the video, try it for yourself, whatever. Make sure that you get that this is the correct final line for this expansion based on these steps. And if you don't, go back and check it out. Okay, what I want to point out to you is this, and again, it might require another pause. Have a look at this line here and have a look at this Pascal's triangle here. Can you see a link between this final line here and what's happening in Pascal's triangle? Pause if you want to. Okay, either you have or you haven't. I'm hoping you might have seen that on the third row, this number here, 3, this number here, 3, and this number here, 1, appears here, here, and here. And what about this? Well, you've got a first term here of x cubed, and the coefficient of x cubed is 1. We just don't normally write it in. We call it the implied coefficient. So there's an implication of a 1 as a coefficient there. 3 is the coefficient of x squared, 3 is the coefficient of x, and there's a 1 at the end here as well. So when we look at these now, we've got 1, 3, 3, 1, and we've got 1, 3, 3, 1 on the third row for an expansion of a cube. So that's great, isn't it? It means that we don't actually have to do all of this hard work if we can see the pattern. That if we've got a power here to the power of n, we would go down to the nth row, and these numbers would give us what I call the starting coefficients. The starting coefficients. When you look at the x from here, we've got x cubed, x squared, x to the power of 1. That's another implied, this is an implied power this time, x to the power of 1. And even here, I'll write it in as well because I wouldn't normally. We've even got x to the power of 0 here. I'll do the implied 1 here as well. So we've effectively got, in terms of the powers, the x is just there. 3, 2, 1, implied, 0, implied. So we've got a perfect pattern here. If you want, pause the video and have a go at doing x plus 1 to the power of 4 and see if you can do it. Either you did or you didn't, and I'm just going to do it now really quickly. So I've got 1 multiplied by x to the power of 4 plus 4 multiplied by x to the power of 3 plus 6 multiplied by x to the power of 2. Can you see how I'm just reducing the powers one at a time? Plus 4 multiplied by x to the power of 1, which I'm not going to write in because I don't need to, plus 1 multiplied by x to the power of 0, which I'm not going to write in because I don't need to. So we've got 4, 3, 2, 1, 0, x to the power of 0, 1, 4, 6, 4, 1 from the fourth row because it's a power of 4 here. Okay, awesome sauce. Let's make things a bit more complicated so we can figure some more stuff out. So this time we've got x plus y to the power of 3, and x plus y to the power of 3 is different from the other one because we've now got something different, something other than 1 as our second term. So x is our first term, y is our second term. Here's the Pascal's triangle that's been generated to the third row because I've got a power of 3 here. Now what I've got over here is I've got the same sort of methodologies I did to start off with in the other problem. I've just gone ahead and done it to save time in the video, and that is I've got x plus y all cubed broken down into x plus y times x plus y squared. I've then used a perfect square expansion to get x squared plus 2xy plus y squared. I've then chicken beaked it like this, and then I've gone, that's x cubed, 3x squared y, 3x squared y, and y cubed. And again, hopefully you can see that the coefficients, including some implied coefficients, like that one there, the starting coefficients, 1, 3, 3, 1, should put that in as well, are the starting coefficients from the third row of Pascal's triangle. The first term, x, has gone down in powers, 3, 2, 1, and then it's disappeared. So that's x to the power of 0 here, which I won't write in this time. But have a look at the second term now. The second term has gone from y to the power of 1 implied. Maybe I'll write that one in just so that we've got it. I'll do that one too to keep it even. So we've got y to the power of 1, y to the power of 2, y to the power of 3. And implied, we've got y to the power of 0 here, which I haven't written in. So we've got 0, 1, 2, 3. So the first term goes down in powers, the second term goes up in powers. Okay, so if I was doing Pascal's triangle, I would go, that is equal to, I'll do it in black, that is equal to 1 multiplied by x cubed y to the power of 0, which I wouldn't write in, plus 3x squared, gone down a power, but now I'm going to go y up a power, y to the power of 1, which I won't write in, plus 3x to the power of 1, and I don't write the 1 in, and I'll go y to the power of 2. I've increased y to the power of 2, plus 1, y to the power of 3, because x is to the power of 0 and therefore disappears. And P.S., I wouldn't even write these 1s in, so it would just look like that. And you're done. One last thing for this video, and then the next video will tackle some more tricky terms inside to make it a little bit more, so you can sort of see how to do it when it's a bit more complicated. What happens if we have x minus y all cubed? Well, it turns out everything's okay. There's a couple of ways of looking at it, but I'm going to break it down for you so you can sort of see it quite easily. What I'm going to point out, though, is that when you subtract something, it is the same as adding its negative. So x minus y all cubed is the same as x plus negative y all cubed. See what I've done there? I've just got the minus y and turned it into a plus minus y. Okay, once you've done that, then all the stuff that you've done up until this point holds true. We just need to be careful with negative numbers when they're raised to a power. I'll show you what I mean. We're going to follow the rule out. So I'm just going to expand a bit so you can sort of see that Pascal's triangle thing there. And I'm going to go 1x to the power of 3, as we normally do, and I've got the 1 implied here, but not needing to write it, plus, and then the next starting coefficient is 3, so I write 3 down, and then I've got x, I don't really need the brackets, do I? 3x squared, but you do need the brackets for for negatives. So multiply by minus y, plus 3x to the power of 1, I'm not going to write the 1 in, multiply by minus y to the power of 2, plus 1, which I'm not going to write down because I've got something else to write there, minus y to the power of 3. Okay, so again, the trick is you've got to have brackets around negatives to make sure that the powers work properly. Now, the next line is just to finally finish simplifying. And the only thing you need to be careful of is what happens when I raise a negative number to a power. Let's say negative 2 to the power of 3. So if I have negative 2 to the power of 3, we know that's negative 2 times negative 2 times negative 2. And negative 2 times negative 2 is 4. So we'd add 4 times negative 2. And we would have 4 times negative 2 equals negative 8. However, if I have, say, something like negative 2 squared, that's negative 2 times negative 2, which is positive 4. What's my point? If you raise a negative number, I meant to circle that with the pen instead. If you raise a negative number to an odd power, you'll get a negative result. If you raise a negative number to an even power, you'll get a positive result. So that means that for on slide 7 there, as I'm simplifying, we just need to check whether the power that negative y has been raised to is even or odd. So we've got an x cubed plus 3x squared negative y. Oh, hang on, that's an odd power. It's raised to the power of 1, which is odd. So that's actually going to be 3 times x squared times negative y. So this whole term is negative. So instead of adding it, I'm going to be subtracting 3x squared y. The next one is minus y squared, which is y squared. So the whole term is positive, so it's going to be plus 3xy squared. And then the last one is minus y cubed. We're raising it to an odd power, so this is going to be minus y cubed. So the final one is minus y cubed, like so. So we've got, what we end up having is, because in our terms, we're going to go from 0 to 1 to 2 to 3 with our second term here, we're going to end up having even, odd, always. And so we're always going to be positive, negative, positive, negative. And you can see it here, positive, negative, positive, negative. So in summary, for what happens when we've got two things subtracted, is you can either always just turn it into a negative and then just follow through like I've got here, and then you won't go wrong. Or you can remember the simple rule, I suppose, is that when you've got two terms subtracted raised to a power, then you have to alternate the signs, positive, negative, etc. So as long as you follow that through one way or the other, you'll always get the problems right. Okay, that'll do for this video. Stay tuned for the next video for more examples.